Welcome to the General Chemistry Fundamentals series by MCAT Genie. And in today's video, we're going to discuss a brief history of atomic theory, and then we'll focus more on atomic structure as we understand it now. But we're going to talk about the development of atomic theory briefly, because it's important to know that when it comes to humans, we don't have the ability to explain nature as we typically think. The reason for this is because we are natural beings ourselves and we did not create the universe. We are creations of it. Therefore, our only ability to understand nature is our ability to describe what we can observe and what we can materially test. And the assumptions that have been accumulated, which are cumulative over time, are going to result in the different theories and models that people are able to come up with. And what is accepted at one point in time may not be accepted later on. So, why don't we start off with where the term atom comes from? And if we go back to the ancient Greek philosophers of the 5th century BC, you'll find out that there was a term called atomos, which they were using to describe the small finite particles that make up matter. And this is what they argued. Now, atomos is a term derived from the Greek word for indivisible. So at that point in time, they thought that atoms were indivisible, but later on, we come to find out that atoms are composed of subatomic particles. However, why don't we start with Dalton's theories, which are very important in our modern understanding of atomic theory. And although it wasn't complete, there were elements of his postulates that we still use today. So why don't we go into detail on Dalton? So if we take a closer look here, I put a few pictures associated with Dalton, and the ones that I have here are to help explain one of the postulates that he had said, or a few of them. So ultimately, what Dalton was getting at was that when you think of any macroscopic piece of matter, in this case, let's look at the penny and let's assume it's fully made out of copper, which it's not. It's about 95% zinc, but let's say copper. And if we have a copper penny, 100% copper, then we should expect 100% copper element or copper atoms that make up that element. And so this is something that we naturally take for granted now, but Dalton was the first one to make this statement, and this is still true. And if we look at copper oxide, copper 2 oxide, well, because copper 2 would be copper 2 plus, and oxide has a 2 minus charge, you can expect that that ionic compound is going to be 1 part copper and 1 part oxide. And when Dalton was doing his experiments, he would notice that proportionally the mass of copper and the mass of oxide would always be multiples of 1 to 1. So that means that compounds are created from proportional or ratios of different elements, and that each element must differ in its chemical structure in some way. So now that we've understood what Dalton was getting at and we have a basis, well, in 1897, Thomson used what's known as a cathode ray. And through the cathode ray experiment, which it's interesting to know that electricity had long been known about, as well as static electricity and charges due to Benjamin Franklin and previous experiences by other people. But electrons were first discovered by Thomson because of this experiment. So, how does the cathode ray experiment prove the existence of electrons? So what would happen is a power supply with high voltage would be used, and the cathode would shoot a beam, which was called a cathode ray beam at the time, but today we know as an electron beam. And that would move towards the anode because the anode was positively charged. And so the cathode ray would go through the anode, and then there would be a magnetic and electric field, as you can see in the middle of the cathode ray gun here. And what was noticed was that the ray or the beam would deflect. Its trajectory would not stay straight when it passed through the electric field. So what this indicated was that because it moved towards the positive terminal of the electric field, then that means that the cathode ray must include negatively charged particles, and this was the basis of where the electron came from. So then in 1903, Thomson moved on to develop his plum pudding model, which you may have heard about before. And if you do remember, the plum pudding model is not consistent with anything that we talk about today. But what he had understood was that atoms are neutrally charged in ground state. and therefore there must be electrons and positively charged particles within the atom. And his idea was that the electrons were just randomly dispersed through the positively charged matter and that they canceled out each other's charges. So now let's introduce Ernest Rutherford, who is significant in that he was able to discover through the gold foil experiment that if you shoot alpha particles, which if you've studied radioactive decay, you'll remember that alpha particles are essentially the same mass and atomic number as helium. So they're decayed particles that would come about as the result of radium decaying. Anyways, these alpha particles, which are known to be positively charged, would have to go through the gold foil. And what would happen is that a majority of the alpha particles would be unhindered. However, a very small amount of the particles would be slightly deflected. And what this would indicate is that there was a positively charged and mass containing nucleus that was causing the deflection of these alpha particles. So if we slide over to the right here, then we'll notice that when the gold foil experiment was performed, the Thomson model would have expected the alpha particles to go through the atom with no hindrance. It would just go straight through, and all of the alpha particles should end up at one point. However, the observed result validated Rutherford's model, and what you would see was what we had mentioned, that a majority of the alpha particles are unhindered. However, some of them would get deflected, and this indicated that the atom was mainly empty space, and there was a positively charged nucleus that contained the majority of its mass in the middle. And so the Rutherford model is our very stereotypical, what you would envision from Jimmy Neutron, for example, electrons flying around the nucleus. But after Rutherford came Niels Bohr, and the interesting thing that Niels Bohr had discovered was that the electrons are not just randomly arranged outside of the nucleus and whirling around, but in fact they're arranged in energy levels, and these energy levels are quantifiable. And Bohr was able to demonstrate this definitively through the hydrogen atom. And he showed that n equals 1, n equals 2, and n equals 3 were definite, different energy levels. And the electrons that were located in these energy levels had the ability to be excited if, let's say, photons or electromagnetic energy was absorbed by the atom. Then you can be prepared for an electron to rise to a higher excited state. And if that electron drops back down to its ground state or its original state, then as you can see here, there should be some type of energy emitted, and that energy would likely be a photon. So Bohr was able to combine Planck's work with Planck's constant and the photoelectric effect, and he was able to explain why that would occur. And this was revolutionary at that time, but Bohr was still missing something, which brings us to what we have today, which is our modern understanding of the electron, and that is going to be through the quantum mechanical model. And so, with the quantum mechanical model, which was built off of the findings of Bohr, what we come to find out was that other scientists such as Schrodinger and Heisenberg and de Broglie provided very important information to us through their research, through the wave equation, through Heisenberg's uncertainty principle, and so forth, that electrons are not just particles. The same way that photons, as Einstein had demonstrated, are both particles and waves, electrons are also going to have particle and wave behavior. And this was easily noticeable through experiments such as the double slit experiment, which you can see in the middle here. The double slit experiment showed how similarly, I want you to imagine two boats traveling next to each other, and the boats will have a wake that goes behind them, and those wakes will spread. And the spreading of waves naturally is called diffraction. And so if you have the double slit diffraction going on and the waves want to spread out, then what you would notice on the other screen, which is picking up the spectrum of the light that gets through to the other side, you notice an interference pattern. And the interference, there are two types, right? So there's constructive interference, where you can imagine two waves coming together and forming a larger wave, or destructive interference, meaning two waves come together and cancel out. We'll talk more about in phase, out of phase, and interference and diffraction when we go through diffraction in a different video. But for the time being, what I want you to understand is that electrons exhibit wave behavior as well as particle behavior, and they are influenced by light. So trying to observe electrons actually interferes and influences the behavior of the electron. And something that Heisenberg had figured out was that when you try to measure the position of an electron, you lose the ability to be certain about its speed. And when you try to measure the speed of an electron, you lose the ability to be certain about its position. So, this conundrum makes it quite difficult to ever predict with any certainty where and how fast an electron is moving at any point in time. But what we can do is form an electron cloud probability. And so the image over here with the pink and blue bubbles is supposed to represent some of the subatomic orbitals, such as s, p, d, and f, which we will talk about much more when we get to electron configuration. But ultimately, when you look at the s orbital, which is lower in energy than the p, which is lower in energy than the d, so on and so forth, you can notice that there are three-dimensional axes, right? That's why it's called three-dimensional. So there's the X, the Y, and the Z. And the S is a spherical cloud that orbits around the nucleus. And then the P electrons are not going to be in that region, but they're going to be outside of that region. So you can expect them to be in the X, Y, and Z axis respectively. And it gets more and more complex as we move forward. You don't have to memorize this, but it is good to visualize this to know that these represent the probabilistic position of where an electron could be based on its energy level. So not everything Bohr said was wrong. Some of the things that Bohr said actually still stand true today. The only issue was that Bohr's model was only able to predict for hydrogen and was not able to predict well for elements with atomic masses and atomic numbers greater than one. Now, this brings us to atomic structure. So with atomic structure, we're mainly going to talk about the properties of the subatomic particles. So we figured out that electrons have very, very, very small masses, almost negligible. However, their charge is equal and opposite to that of a proton. So therefore, we expect atoms in their ground state to have the same number of electrons and protons. From the proton count, which is known as the atomic number, we can determine the identity of the element that we are looking at. And as soon as the atomic number changes, then the element or the atom that we are discussing is different. So the atomic number or the number of protons is essential to identifying what an element or an atom is. When we include the neutrons, then we'll be discussing the uncharged or neutrally charged, but very approximately close to proton in mass subatomic particles. And so when you take the mass number and you subtract the atomic number, then you can expect to find the number of neutrons. And if the number of neutrons changes, then we are looking at a different isotope of that element. So when the isotope of an element is different, that actually changes the potential radioactivity and the decay that will occur with that atom because it changes the stability of it. As you'll notice on the periodic table, the mass number for any element is typically not an integer or a whole number, and it tends to have a decimal after it. And the reason for that is because there are multiple isotopes that naturally occur for each element. If you take into account the percentage of the time that that element appears with that isotope, and then you add that up by multiplying that by each of the masses, you can find an average atomic mass for each element. We'll discuss that further if necessary in another video. And last but not least, if we change the number of electrons, then we won't be changing what element it is. We won't be changing what isotope it is, but we can no longer call that an atom because an atom is only true in the ground state when the electrons and the protons are the same. So if we change the electron count and it becomes less negatively charged, meaning we take away electrons, then therefore we can call that positively charged. And so this helium, if it had a 2 plus charge, which is quite uncommon, would be called a cation, positively charged. And conversely, if we add extra electrons and we form a negatively charged ion, then this is called an anion. And the easy way to remember this is that cation has a T in it, which looks like a plus sign, and this is positively charged. And anion has an N in the prefix, which N is the first letter of negative, and which means anion is negatively charged. Both cations and anions will be very, very important to understand for multiple lessons down the line. So it's very good to be solid on that from this standpoint. I hope that this was a good fundamental overview of atomic theory and what we know about atomic structure so far. We'll go into further detail about electronic structure, electron configuration, the periodic table, and the trends in the periodic table in further videos. And thank you for watching.